Well over. In Uganda, it's already 1857, that is 6:57 p.m. I think in Japan could be more or less almost midnight, and other parts of the country, the world. This is your friend, your brother, your colleagues, your practitioner, Engineer Michael Chola. I know I've taken long, but just I think we are still in our transition into the public service. But I've been trying to think aloud in regard to modeling abutment. And in most cases, we do elastic approach. We don't take into consideration the issues of construction staging and also the issue of shrinkage, creep, and the rest of it. So what I've tried to learn today was to try to model this bridge. Do your piling, then later on do the pile cap, after which you get into the abutment and you complete with the ballast wall. Then you apply the loadings, and you see how the loads get built up, kind of, in terms of deformation and loading. So you do your normal modeling, which we have done. And this bridge I did, this abutment has a square depth of up to 17 meters. Of course, this is a calculation from hydrologist. It is 17, no, it is about 13 meters is the pile length, then 3 into the rock, but the square is about 12.6. So if you round up and then you get into the rock, you have about 16 meters. So definitely in the model, you have to ensure that this overburden soil between the pile cap all the way down to about top of the bottom of the square, which is top of the rock, is free. You don't have any soil structure interaction, no subgrade reaction, no spring, and therefore that means the stability is actually anchored into the rock. And if you look at the support, the way it is done, the spring, the linear spring, you find this is basically that. So that is what you do and you apply. So there's that stream flow, which will also be here. And then this is now, of course, at the construction stage, as soon as you are done with construction, you still have a scenario where this spring constant is up here. Then over time, scoring begin to happen. 10 years, 15 years, rapid flow, scoring will continue until the top of the rock. So below which now you have to do the embedment. So if you do the design using those Tomlinsons and other models, basically you should be able to get the skin friction of the rock and other things so that the stability is held, is basically down here. While you have loads applied up here like soil pressure. You see soil pressure is here. You have soil pressure onto this abutment, pushing it the bridge length and also acting on this wing wall. Even the hydrostatic pressure, you come to dynamic pressure from from seismic. Recently, we had seismic tremor here in Uganda with epicenter around Nakasongola, and the PGA was about 0.02 with the magnitude of about 4.5. Definitely, of course, we shall get the final better output, a better result from the Department of Geology and Mines, so that we understand that. But normally in our design, we consider the PGA of about 0.03 is the central region, because that's basically the mile region, our active faults lies along the western axis, western region, and eastern. So basically this load will be applied, but these piles will be able, at a later date when the scoring has happened, should be able to withstand all these loads. So that is how. So you have two case scenario to do. You model when the foundation. You can actually have three case scenario. You can have case one when at the commissioning of the bridge, when you are done with the construction, the river training is done well, river bed invert level is still okay, therefore your spring constant is all the way up here. Then maybe out of 10 or 20 years you can take a 5-meter score, you run an analysis, see the implication, then you run another 50 years, and then when it is about 75, then you do a complete one. So you look at the scenario. Maybe at the end of it all, you look at the impact of push-pull effect, the pulling effect, the stability issues, and then you strike a balance. But I have just gone to the worst case scenario to have a look at this. So with this, what I wanted to look at is how do I admire my how do I admire the build up of these elements. I have pile first, pile cap, abutment on wing walls, and then the ballast, and then the loading. So if I look at construction stage 1, I do my encasing of piles, and I can also look at the deformation. So this is the self weight of this pile when you have done when you have now inserted the piles. Then of course at the moment now at the construction stage, this is not what you have. And what I would have done is to have this spring constant all the way up here, and then the second one I would now bring in my pile caps. So I think to have it look nice, what I would do is to first remove the spring constant. So this is my first stage. I construct it, put my all. Normally you have to look put the boundary conditions. Self weight will be at the loading stage. You have the self weight, then you have the boundary condition must be put in place, and then the elements or the subgroup, which will be the pile. So under construction stage 2, I have now brought in my pile cap in place. You can now see even the implication. Immediately you can see you begin to see the implication of punching onto these piles. You can see. So now the weight of so now the reaction down here would be accumulation of the weight of pile caps and the self weight of the piles. Then stage 3 is when you have all these are in place, except because if you are to launch if you are to do the launching of the deck girders, you need to have a drive until you do all the launching. All the girders are in place, then you put this reinforcement up and the ballast wall is constructed. That is why you are able to see that this is what we have, and you can actually even look at what they call then the last stage, which is the stage number 4, you have now this the last one, and the weight continue. Then now all of it, now if it is all in place, then you are able now to, that is stage 5. So this construction is done. We have now completed it. It is now like has even gone more than 3 months. It is of course normally you see like maybe 10,000 days. You have gone during the construction period, you find you can even go after like a year or 2. But these culverts, these bridges go after about 3 years. So you'll find after you are done with culvert will remain hardening. It will now the 14 days, the 28 days, the 100, so it goes always. So now this is the deformation when it is completed. Now we have not actually even applied your loading. So if you are to apply now the different loads, then definitely now we go to the post-construction stage. So this is the self-weight of these of the deformation due to self-weight for this abutment. If self-weight. But now if I have the deck loading, which I have imported from my deck, that's how the whole thing will behave. The deck loading will happen, will work, self-weight, deck load. Now you can actually look at the implication of push-pull effect. You see the stress distribution even in the pile is not actually the same. If I say, let me look at the live load surcharge, which you apply on the wall, definitely it is a completely a different setup, and I can actually also could actually also look at the forces, the stresses, and then you see how the stresses are built, and then so that can give you a bit of so basically this is how the stress built up, you can see. So if we were to go back into the construction staging, normally for episode when it is number 2, this is how you would actually look at the stress distribution, the shearing, and then construction 3. So the stress begin to build up as you continue adding the different elements until you are able. Now this is now when it is basically after you are complete construction and you are able now to load the structure. And the loading of the structure is basically is actually in the post-construction stage, where you actually have to now I think what I will do here is to make sure I think my deformation should first get back, and then I look at the then if I'm to look at the stresses, I go to the plate, and then I'm able to look at the different loading. I told you I can actually look at hydrostatic pressure or vertical pressure or soil pressure or dynamic soil from earthquake. That is how the whole thing works. So you are able to view. So the construction staging, you have seen how it was built up, and definitely if you want to see the built up, that is what was done. And also you can also look at the different applied loads, especially if we are to do this one from load case 1, no, construction stage 1, you are able to see the moment built up, the beam diagram. So let me see, let me look at the reaction first. So reactions, we have it here with the value. So this reaction, now this is more of you are able to get your tip resistance and also the friction here on this pile. So this is only when pile is put in place. Then you can also look at construction staging 2, and then you see the shift in the what? The shift in the loading. Here you can now see you have weight distributed, and then you are able to look at all that. Even when you are to look at the different moment diagram, you should be able to look at the moment diagram of these members. This is when the pile cap is in place. Supposing the pile cap is not there, I'm able, so that it's very minimum. I think what could be clear here could be the set now we need to understand something. I will try to update and do the series properly. This is more or less at the last stage, where that's why it is only appearing down. But I will be able at the construction where there's no scoring, it will be all the way up here. So for now, you find it is not up to up, and so we are able to only view moment distribution and shear and the rest of it. Now when now you add the piles, and then the stage 3, when the abutment comes in place, you see the moment values are all increasing here, and then by the time you are done with at the construction, when the construction is completed, you are able now to look at almost 1,000, almost 2,000 kilonewton here. This is basically what you have at the end of construction stage, and basically 4-5 years, 3 to 2 years or 4. Now, but when you begin to apply the loads now, like you have done all these other loads, that is the under post construction stage. Now this is only for self-weight. Now in your self-weight, you can see that the behavior of this is basically different, because these piles have different behavior based on how they are loaded. And then if you try to put in a bit of lateral load, like if I do when you apply soil pressure on this abutment, definitely you are going to see all that. And so the different loading and different stages have different response and then cumulating. So what I appreciated more here was for us to be able to appreciate that construction stage load built up. It takes care of both shrinkage. You can see I have creep, I have the dead load, of course I have the creep. This is creep. So creep is taken care of in your design, and then also shrinkage should be able to be taken care of. So this is normally what we need to be doing, even when we do buildings and anything. You do construction staging, so that both creep, shrinkage, based on the temperature effect, are all considered. That's why I was a bit very, very concerned that we need this is summation of both. So at the end here, you are able to see that all this creep, shrinkage, all that are taken care of and are part of this. The same I think would apply when even on let me see if it can, so this is your stress generated considering both the dead load without applying these other loads like the deck loading, the soil pressure, hydrostatic, the dynamic from earthquake. This is basically self-weight, but shrinkage is there, and also creep. And shrinkage is an element of temperature effect and the rest of it. So you are able to see all that and can look at it. These are the stress built up. So it's very, very important that we consider construction staging. That's what I'm interested in. Construction staging is what I'm trying to look at, that actually at every stage I should be able to build a case, an element case by case, to be able to so when I have if I have my pile is put in place, then later on I expect this deformation, which is contour. That is what I would expect at the first place. Then in the second place, I look at how all this happening, and then creep and shrinkage begin to take shape, and then I correctly monitor and manage the structure without coming up with surprises at the end of my construction stage. And this is now exactly what I'm trying to look at. These are built up deformation. You can also look at the stresses I've given you, and even then later on you can apply. So basically this is what I thought I should share with you, just to appreciate and then try to emulate, especially my young engineers and those who are getting into bridges. So if we can appreciate environmental loadings and the rest of it, we should be able to do that. So this is if this is the ultimate limit state, when you applied all the loadings and you want to see the behavior of this structure. And then if you want to look at the deformation aspect, you should be able to view how this thing moves. And then now there are things we need to look at. This one I have not applied in the, this is only when you have a push in the bridge's direction. So you have a push effect here and the pull effect. All that need to be assessed during your design. You have to check all this, because this pile can actually tear, or this tension here, while here is heavily compression. So you have to be careful. Sometimes even the bearing capacity may not be able to take on, so you do that. You check the push-pull effect, and then in event that you have applied if you have applied maybe a lateral load kind of stuff, so you should be able to, yes, so here the loading will definitely look different. You can see we have this, and I want to see if I've applied dynamic will always go in that direction. Let me look at the temperature effect. How does the temperature effect behave on structures? You know, we think substructure do not undergo deformation under temperature, but if you look at it, definitely undergoes. You can see contraction and then expansion. This is more of contraction. And then if I look at a maximum temperature, and then you apply only on the upper part of on the upper part of the abutment, then you see this is an expansion kind of behavior. So this is the more of an expansion behavior. And then when you go, so this affects your response, and also can create cracks. It adds into the moment of that means there's some element of reinforcement that need to be added. So this is more of expansion effect when the temperature is slightly high, and this becomes a contraction effect when the temperature is low. So that's how the whole thing behaves. And so expansion, contraction, and it also affects the behavior of the deck system and also the bearing area and the rest. So this is basically temperature. So if you now look at a global where you have applied these loads, all of it now, that is why now both temperature is there, what is there, then it behaves as an looks at the effective, the resultant load kind of. So if you look at this, we have the braking force here from the deck dead load, deck live load has got also element of braking. So in a way, an effective behavior. Now that's where. So this will generate some movement that need to be taken care of, whereby your expansion joint and other support system also will be taken care of. This is basically, I was just trying to appreciate I was trying to appreciate the effect of of effect of the effect of I'm trying to appreciate if I'm to look at what we call, if I'm to look at only the construction staging, this is what I will see. Yeah, so that is what I will look at. That is how. So there is also that effect, and then I can add on the animation will definitely continue to behave depending on what we have added. So if I add this, then you will see the behavior. So it has a different response criteria. You see, so that's how the whole thing would respond. And then if you put your third level, the abutment is in place. Then you apply that, and then you do that. We are not into the, this is the amount of force we are applying. We're just trying to appreciate that. Actually, it is very important that you take note. You see now, once you add on the third stage, which is now the abutment, and this before you have added your ballast wall, you can see the implication. The deformation already increasing here, almost by 0 point something. So we need to take note. We need to appreciate and try to do some of the things in a better way. That is what I could actually say, and yep, I think that is as good as greeting you. I've just greeted you. And so I think what we need to do is to close this, and then we are able to stop. Yeah.